Hey guys, okay, so let's have a look at section 5.3 in our notes. This one's about parallel circuits. Before I do get cracking though, please don't forget that with the series section, I forgot to tell you, exercise set 4 question 2. Make sure you do exercise set 4 question 2, okay? Right, so parallel circuits, different obviously to series circuits because it's stating the obvious here, but obviously there's two or more pathways. So if one of the pathways breaks, the other ones can still function. So as we did for the series circuits, we'll look at what the current does, what the voltage does, and how to work out the total resistance. It's almost sort of the opposite of what the series circuit does, but we'll look at them and you'll see what I mean. So first of all, the voltage, or in other words, potential difference across each branch, instead of being different, or the sum of the potential drops is equal to the EMF. Pardon me. With a parallel circuit, the voltage across each branch is the same as the EMF. So if I have a look at this diagram up here, so like if I've got, say, 12 volt battery, I've got 12 volts across there, 12 volts across there, 12 volts across there. Between, I'll call them point A and point B. Not surprisingly, there's 12 volts. Between point A and point C, there's 12 volts. I kind of liken it to, if you've got like a car battery, here's my drawing of a car battery. That's probably better. Just making a hash of it now. There's a car battery. So there's the two terminals, 1, 2, and that's 12 volts. If you're doing a parallel circuit, think of like it's just extending those terminals out and being able to, across those terminals, put, like a number of branches. So I'm doing like light globes. So for example, each one of those light globes would have 12 volts across it. So think of it that way. So first rule in terms of voltage is the voltage across each of the branches is equal to the EMF. Now, the current, on the other hand, of course, if I get rid of all the stuff that I used before, the current, on the other hand, is what kind of breaks up into pieces. It's a bit like a reticulation system. I'll use an example here, nice easy one. If I've got, say, like 9 amps going through there, and I'll call that our total current. All right, let's just say I picked a number 9 amps. When it gets to that point there, what it's going to do is, just like a retic system, it splits up into I1, I2, and I3. So the current that goes in each of those branches is, first of all, going to be inversely proportional to the resistance. But if we make it nice and easy, if R1 is equal to R2 is equal to R3, then the current at that point is just going to break up into 3. And then when it gets to, say, point B over here, it's going to recombine again. So if I took a reading there, it would read 9 amps again. So Kirchhoff's second rule for current, directly applies to this, where if I've got 9 amps coming into a point, I'll have 9 amps going out. It's just how it's distributed, it's different. And like it says down here, you've got the total current is the sum of the currents in each of the individual branches. Okay, so there's voltage or potential drop, and they're equal to the EMF, and then of course current divvies up. Now, a formula that gives quite a few people a bit of grief is how to work out the equivalent resistance of a parallel circuit. I'm not going to annotate this and read through all this. If you want, pause it now, read what it says here, because especially we're applying what we just learnt up here, up the top there. We're applying what we learnt just there, and we come up with this formula. If you like, pause it now, have a read of that stuff there. Now I'm assuming you've come back, and what we should find is that the total resistance is equal to the inverse sum of the inverse of the individual resistances. And there's that term again, the equivalent resistance. The thing to remember here is effectively what that's saying is that the total resistance is inversely proportional to the number of branches in a parallel circuit. So if I went back up to my awesome drawing of a 12-volt battery, the more or the longer I made these terminals, if you like, if I made them super long up to there, okay, and the more of these light globes I added, in fact, the less the total resistance would be. And if you think about it, it's got to kind of make sense. The more light globes I add, if each one of them has got 12 volts across them, they've all got to be of equal brightness. If they're all of equal brightness, the more I add, the less resistance there is, so the more current has to flow to keep them so that you can divide up into however many of the light globes you've got and keep all of them equally bright. Consequently, as the resistance goes down and the current goes up, of course, the battery will run out faster, which instinctively would sort of make sense to you, wouldn't it? The more light globes you add, the quicker the battery will go flat. So this formula here, the equivalent resistance in a parallel circuit, we'll go through an example of that one. So we'll skip example 1 and we'll go straight to, I think example 3 is a good one. Actually, sorry, example 2, we'll do that one very quickly. Zoom in a bit, and okay. The equivalent resistance of 3 20s. 1 over 20 plus 1 over 20 plus 1 over 20 and a 10. Okay. The equivalent resistance is the inverse of all that. So 1/20th and 1/20th and 1/20th is 3 20ths plus effectively 2 20ths. What does that give us? 5 20ths. And so the inverse of that, of course, is 20 on 5, which gives us 4 ohms. So what it's saying is if I've got 3 20 ohm resistors and a 10 in parallel, I could replace all of those with a single 4 ohm resistor, and it wouldn't make any difference at all. It's all good. Okay, let's hit example 3. And okay, you can see this is a pretty typical question because it's sort of breaking it up into parts. So I'll go first of all the total resistance. They're in parallel, so you've got 1/20th plus 1/5, inverse of that. Last common, so multiple is what you want to use here. So 1/20th plus 4/20ths. The inverse of 5/20ths is 20 over 5. Ooh, surprise, surprise. That's again 4 ohms. Oops, the inverse there. Just double check 20 over 5. Yeah, 4 ohms. So the total current, number 2, the total current is, again, straight onto Ohm's law. The total current is V on R. The total resistance, we got 40 volts, 4 ohms, so it's going to be 10 amps. Alright, so your current through number 3, we're going green. The current through the 20 ohm resistor is V on R. What's the voltage? 40 volts. Oops. 20 ohms, so you're going to have 2 amps. Now, here's the interesting part. With the current through the 5 ohm resistor, there's about 3 ways you can do this. Current through your 5 ohm resistor. Remember we said that the current is inversely proportional to the resistance in any branch. So compared to the 20 ohm resistor, we'd expect 4 times as much current. Okay, so it's going to be 4 times the current in a 20 ohm resistor because I've got 1/4 the resistance. So 4 times 2, we're going to have 8 amps. Always check. 8 amps in one branch, 2 amps in the other. Total current was 10 amps, so we know we're right. These questions have always got like an inbuilt checking system. Pardon me. So with that current in the 5 ohm resistor, the second way we would do it, of course, is V on R. We had 40 volts across it and 8 amps. Happy days. Same. Hey, cool. So I won't get into the complex circuits. We'll leave that for Tuesday. But certainly what you want to be able to do now is you should be able to certainly finish off that Hewitt worksheet there, that one there, which is, page 94 from that Hewitt book that I've breached copyright to give to you. And when we look at exercise set 4, actually look, by all means, if you can have a go at section 5.4, that's good. But I'd say probably a good priority now would be to work on exercise set 4, and we'll get there in a second. There it is, exercise set 4. Should be able to do 1, 2, 3 without too many dramas. Should be able to do 5. You should be able to do 6 now. 6 is a good old exam question. You should be able to do those questions, and I'll catch you later. Thanks. See you tomorrow.